NEC section 240.4B addresses the protection of conductors. This section stipulates that feeder conductors supplying branch circuits and other feeders must have an ampacity that is not less than the maximum load they are expected to serve. Additionally, their ampacity must be at least equal to the rating of the overcurrent device that protects the circuit or feeder. Let's consider the application of this code section to service entrances. In the context of a service entrance, a key characteristic is the absence of overcurrent protection on the line side of the service. Consequently, the determination of the ampacity of the service entrance conductors relies on the calculated load. For example, using 500 kcmil copper conductors for a 400 amp service is typically acceptable. This is because the ampacity of 500 kcmil copper to 75 degrees Celsius termination is 380 amps, which can be less than the calculated load for a 400 amp service. Now let's discuss the application to sub-panels. When supplying power to a sub-panel, the ampacity of the feeder conductors must be determined based on the rating of the overcurrent device protecting that feeder. This means the conductors need to be appropriately sized to handle the current dictated by the breaker protecting the sub-panel. For instance, using 4/0 aluminum wire for a 200 amp sub-panel is generally not acceptable. The ampacity of 4/0 aluminum wire at 75 degrees Celsius is 180 amps, which is less than the rating of the 200 amps breaker protecting the sub-panel. In such cases, the feeder conductors must be sized to handle at least 200 amps in order to be adequately protected by the overcurrent device. It is important to consider section 210.3. There is an exception to 210.3 that permits the use of the next smaller size wire under certain conditions. This exception applies when the ampacity of the conductor is at least 15 amps and the rating of the overcurrent device does not exceed 50 amps. However, it's important to note that this particular exception does not extend to feeder conductors supplying sub-panels. When sizing conductors, it is crucial to consider both the breaker protection and the temperature rating of the lugs. For the specific case of a 200 amp sub-panel, it is not acceptable to use 4/0 aluminum wire because its ampacity falls below the rating of the breaker. It is essential to ensure that the conductor ampacity meets or exceeds the breaker rating to comply with electrical code requirement. The correct application of NEC section 240.4B is critical for ensuring electrical safety and code compliance in both service entrances and sub-panel installations. The NEC, or National Electrical Code, provides comprehensive guidelines for safe electrical installations. Understanding and adhering to these guidelines is essential for qualified electrical workers and anyone involved in electrical work. The purpose of the NEC is to protect people and property from hazards arising from the use of electricity. It covers a wide range of topics, including wiring methods, overcurrent protection, grounding, and equipment installation. The NEC is updated every 3 years to incorporate new technologies and address emerging safety concerns. Local jurisdictions often adopt the NEC as the basis for their electrical codes, sometimes with local amendments. Therefore, it is crucial to consult the latest edition of the NEC and any applicable local amendments when performing electrical work. One of the fundamental principles of the NEC is the proper selection and installation of conductors. Conductors must be sized appropriately to carry the intended load without overheating. The ampacity of a conductor, which is its current carrying capacity, is determined by factors such as conductor material size, insulation type, and ambient temperature. The NEC provides ampacity tables that list the allowable ampacities for various types of conductors under specific conditions. Overcurrent protection is another critical aspect of electrical safety. Overcurrent protective devices, such as circuit breakers and fuses, are designed to interrupt the flow of current when it exceeds a safe level. This protects conductors and equipment from damage due to overloads and short circuits. The NEC specifies the requirements for overcurrent protection, including the selection and sizing of overcurrent devices. Grounding is essential for providing a safe path for fault current to return to the source. This helps to prevent electric shock hazards and reduce the risk of fire. The NEC outlines the requirements for grounding systems, including the installation of grounding electrodes, grounding conductors, and equipment grounding conductors. Proper grounding ensures that metal enclosures and other conductive parts of electrical equipment are the same potential as the earth, minimizing the risk of electrical shock. Equipment installation is another area covered by the NEC. The code provides requirements for the installation of various types of electrical equipment, such as panel boards, transformers, and motors. These requirements address issues such as working space, clearances, and ventilation. Proper equipment installation ensures that electrical equipment operates safely and reliably. The NEC also addresses specific requirements for different types of occupancies, such as residential, commercial, and industrial buildings. These requirements take into account the unique electrical needs and hazards associated with each type of occupancy. For example, the NEC provides specific requirements for the installation of ground fault circuit interrupters, or GFCIs, in residential bathrooms and kitchens to protect against electric shock hazards. In addition to the technical requirements, the NEC also emphasizes the importance of proper workmanship. Electrical installations must be performed in a neat and professional manner, with all connections made securely and all equipment properly supported. Proper workmanship not only enhances safety, but also improves the reliability and longevity of electrical installations. The NEC is a complex and comprehensive document, and it can be challenging to navigate. However, there are many resources available to help electrical workers and others understand the code. These resources include training courses, seminars, and online forums. By taking advantage of these resources, individuals can improve their knowledge of the NEC and ensure that their electrical work is safe and code compliant. Remember to consult the latest edition of the NEC and any applicable local amendments when performing electrical work. Understanding and adhering to these guidelines is essential for qualified electrical workers and anyone involved in electrical work. The NEC is a living document that is constantly evolving to address new technologies and emerging safety concerns. By staying informed about the latest changes to the NEC, individuals can help to ensure that their electrical work is safe and up to date. In summary, the NEC provides comprehensive guidelines for safe electrical installations. It covers a wide range of topics including wiring methods, overcurrent protection, grounding, and equipment installation. By understanding and adhering to the NEC, individuals can help to protect people and property from hazards arising from the use of electricity. Now, let's delve deeper into the specifics of conductor sizing and overcurrent protection as outlined in the NEC, particularly focusing on the practical implications of Section 240.4B. This section, as we established, mandates that feeder conductors must have an ampacity no less than the maximum load they serve and not less than the rating of the overcurrent device protecting them. This seemingly straightforward statement has profound implications for how electrical systems are designed and installed. Firstly, let's break down the two requirements embedded within this section. The first requirement dictates that the conductor ampacity must be sufficient for the load it serves. This means that before selecting a conductor, a thorough load calculation must be performed to determine the maximum current that the conductor will be expected to carry. This load calculation must take into account all connected loads, including lighting, receptacles, and any permanently connected equipment. The NEC provides detailed methods for performing load calculations, which vary depending on the type of occupancy and the nature of the loads. Secondly, the conductor ampacity must not be less than the rating of the overcurrent device protecting it. This requirement is in place to ensure that the conductor is adequately protected against overloads and short circuits. The overcurrent device, typically a circuit breaker or fuse, is designed to interrupt the flow of current when it exceeds a safe level for the conductor. If the conductor ampacity is less than the rating of the overcurrent device, the conductor could overheat and potentially cause a fire before the overcurrent device trips. Now let's consider some practical examples of how Section 240.4B applies in real-world electrical installations. Suppose you are installing a feeder to supply a sub-panel in a commercial building. The sub-panel will serve a variety of loads, including lighting, receptacles, and a small HVAC unit. After performing a load calculation, you determine that the maximum load on the sub-panel is 80 amps. In this case, you would need to select a conductor with an ampacity of at least 80 amps. However, you also need to consider the rating of the overcurrent device protecting the feeder. If the feeder is protected by a 100 amp circuit breaker, you would need to select a conductor with an ampacity of at least 100 amps, even though the calculated load is only 80 amps. This is because the conductor must be sized to handle the full potential current that could flow through it before the overcurrent device trips. In another scenario, imagine you are installing a service entrance for a residential dwelling. The service entrance conductors will connect the utility transformer to the main service panel. In this case, there is typically no overcurrent protection on the line side of the service entrance conductors. Therefore, the ampacity of the service entrance conductors must be based solely on the calculated load. If the calculated load for the dwelling is 150 amps, you would need to select service entrance conductors with an ampacity of at least 150 amps. It's important to note that the ampacity of a conductor is not a fixed value. It depends on several factors, including the conductor material, size, insulation type, and ambient temperature. The NEC provides ampacity tables that list the allowable ampacities for various types of conductors under specific conditions. These tables are essential for selecting the correct conductor size for a given application. For example, the ampacity of a copper conductor is typically higher than the ampacity of an aluminum conductor of the same size. This is because copper has a lower resistance than aluminum, which means it can carry more current without overheating. Similarly, the ampacity of a conductor with a higher temperature rating is typically higher than the ampacity of a conductor with a lower temperature rating. This is because the conductor with the higher temperature rating can withstand higher temperatures without degrading its insulation. In addition to the ampacity tables, the NEC also provides dating factors that must be applied under certain conditions. Dating factors are used to reduce the allowable ampacity of a conductor when it is installed in a way that restricts its ability to dissipate heat. For example, conductors installed in conduit are typically derated because the conduit limits the airflow around the conductors, which can cause them to overheat. Similarly, conductors installed in close proximity to each other are typically derated because they can radiate heat onto each other, which can also cause them to overheat. In conclusion, Section 240.4B of the NEC is a critical provision that governs the protection of conductors. It mandates that feeder conductors must have an ampacity no less than the maximum load they serve and not less than the rating of the overcurrent device protecting them. This provision is essential for ensuring electrical safety and preventing fires caused by overheating conductors. By understanding the requirements of Section 240.4B and applying them correctly, electrical workers can help to ensure that electrical systems are designed and installed safely and reliably. The NEC provides comprehensive guidelines for safe electrical installations, and adherence to these guidelines is crucial for qualified electrical workers and anyone involved in electrical work.